maybe 3 lectures. Okay, so that's our goal. So let's start with the characters. Okay, and like with many previous lectures, I'm going to start this one by reminding you of these basic formulas for H. Okay, so you remember that the Cauchy determinant had zeros at these locations H, R, S, and in one of the 3 ways we wrote that formula, the one in which we wrote it in terms of this variable we call T, I think the second way. Okay, the formula took the form H R comma S is equal to 1 by 4 R square minus 1 plus 1 by 4 S square minus 1. This one had a T, this had a 1 by T, and we have minus half RS minus 1. Okay, and the central charge of our theory was 13 minus 6 in a T plus 1 by T. Okay, you remember that in the case of the minimal models, this T parameter was equal to, which way did it go? P by P prime? P by P prime. Again, we're interested in these special values where T takes the value P by P prime. Character as partition function. I'll define it as we go on. It's a complete characterization of the states of the module. So complete counting of states with charges. Yeah, so basically Q to the power L0. A trace of Q to the power L0 is character. Okay. Fine. Excellent. Now, there were 2 or 3 other things that we also discussed that I'm going to just remind you of. Okay, you remember that characters had the following that H, these formulas for H had the following periodicities. H of I think we used to use the first variable as P prime, right? So RS was equal to H P prime plus R P plus S. This you remember. You also remember that HRS was equal to H of P prime minus R and P minus S. This also you remember. And you remember that the characters themselves had null states. That the null states themselves had null states. Right? Which meant that the this statement was expressed by the following equations. That H RS plus RS. So this was the dimension of the null state. You remember the HRS had a null state at level RS.
Yeah, last time I didn't understand this label. Is it R comma S plus?
R comma S. This is H R comma S plus the product of R with S. R and S are numbers, you just take that product. You remember that the state labeled by R comma S had a null state at level RS, R times S. So the state labeled by 5 comma 7 has a null state at level 35. Right, so that's why that RS. Okay, so this quantity was itself an H of this form. Right? And we wrote 2 equivalent, using these periodicities, we wrote 2 equivalent relations for this. This was H of P prime plus R and P minus S. But this could also be written as H of P prime minus R and P plus S. Okay? So the null state First, why are there two ways of writing it? You see, this guy itself had two ways of writing it. So it has a null state at level Rs, but it also has a null state at level P prime minus R, P minus S. Right? Because it's also H, P prime minus R, P minus S. So also the null state has two null states in the same way. That's what this expresses. Is this clear? So this null state will have a null state at descendant level above its dimension, P prime plus R, P minus S, times P minus S, and have another null state at level above its dimension, P prime minus R times P plus S. Okay, that's why there were two ways of writing this. Now, the fact that there were two ways of writing this tells you that H Rs plus P prime minus R, P minus S, that's product of these two, was also another H. Right? Both null states were themselves reducible representations. Okay? And this, we explained, was HR of 2P minus S, which is the same as H of 2P prime minus R, comma S. Okay? This, of course, we discussed in the lecture we had in the math seminar room. Just to remind you of these relations. All clear? Okay? These equations, of course, just equations, but what should be in your mind is what it tells you. It tells you that the null states are themselves reducible representations. And we can find the levels of their null states by recursively using this formula. Okay. So, now we get to the question at hand. The question is, what is the character in the theory with PP prime? So this character will depend on PP prime and will depend on RS. So what does this character mean? This is the question that you were asking, and this is just trace of Q to the power L0. Okay, very simple. Now, we're asking a slightly complicated question. Let's back up and ask a simpler question. Suppose we had a long representation with no null states. Then what would the character of that representation be?
Some dialectic.
It's very simple, because you can act with L minus 1 as many times as you want, or L minus 2 as many times as you want. Okay? So, long characters, chi of long, chi, let's call it long, of Q and just some H. The dimension of the primary is H, is equal to Q to the power H, because that's the dimension of the primary, and then 1 minus Q into 1 minus Q squared, 1 minus, just keep going, right? That's clear, right? Because you get a Bose factor for L minus 1, a Bose factor for L minus 2, a Bose factor for L minus 3, and just keep going. That's clear. So had we been doing long representations, the characters would have been trivial things. Okay? But we're not looking at long representations. We're looking at short representations. Remember that when we've got short representations, I mean states, representations with null states, the way we're going to make the theory is by removing the null states. The null states will not be part of a theory. They're thrown away. They're thought of as like equations of motion. Okay? Therefore, your first guess might be, well, if we momentarily forget the fact. Okay, your first guess might be that chi p prime rs. Okay, you might think will be chi long of here this also depends on C. Well, not really, but okay, fine. This could be chi long of HRS of Q minus chi long of the two H's associated with the null states. That is HRS plus RS minus chi long of HRS plus P prime minus R, P minus S. Right? Because you might think, okay, what you have to do is to remove the null states. And had the null states themselves labeled long representations, this would have been correct. Because you would have had all the null states all the states you would have had, except you have to remove some states. But the problem is that the null states are themselves null. Okay? And so this is not quite correct. We've subtracted too much. Now, that we've subtracted too much is not completely obvious. It happens because of the following thing. See, that we've subtracted too much just because this guy was, you might think, well, I've got this null state. Now this null state has extra null states, but I want to subtract them anyway. So it's okay that they were short. I mean, doesn't matter that they were short. If I just regard whatever I had to subtract from that as things to be thrown away, that would be okay. And that's right. However, there is a problem. And the problem is, sorry, first, is this clear? Sorry, let me say it again. Let me draw a diagram. That will make it clear. Suppose I had these nulls, this module, and I need some color. Okay, there is no color. Fine. Doesn't matter. Okay, we'll do without color. Okay. Now suppose this guy had a null state here, and it looked like this. This was null state number 1. This guy had a null state. We know there are 2 null states. And it looked like this. I want to subtract away all the states here. Now, if this guy also had some null states, I don't care. I want to subtract them all away anyway. Right? All of those have to be thrown off. So, had this been the only issue, that's okay. But what is the danger? The danger is that these two guys are not non-overlapping. Now, when can two things be not non-overlapping? You see, suppose you've got a primary and you build states on top of that primary. If you can go back down, you start with the state, you go up. If you can go back down, you'll know which primary you came from. It can't come from 2 primaries. The place where you can overlap is when your primaries themselves, your representations themselves have null states. Because those null states are placed, the descendants of those null states, you cannot go back down further than the null primary itself. Is this clear? So the danger is that this structure could have overlapped like this. And maybe multiple times, but each time this happens, the place where this overlap starts has to itself be a null primary. Okay? So question. So this is what makes this problem complicated. Is this clear? When the null states have null states, it's possible that the null states of the null states overlap. Okay? So we want to find when this whether this happens in this case or not. Is the question clear?
So we have to add those 2
We'll discuss what we have to do. First, we have to discuss. We have to see whether this happens or not. Then we'll discuss what to do with it. Yes.
Whenever two line descendants overlap, we have a null primary.
Yes, exactly. We have a null primary. Exactly. Okay. A null primary of the null descendants. You know, the second level primary. Okay.
Why should it be null primary? Because you are saying when there is an
With
ambiguity to go.
yes, then you can't go down further than this. It's because you act with.
It should be a primary.
That's why it's only primaries you cannot go down further. Okay? If you could keep going down, you trace it down to the lowest guy. It would be this guy or this guy. Right? Okay. So the places where these guys overlap have to be, the lowest state has to itself be a primary of the primary. A null primary of the null states. And of both of them. Yes?
Having a null state inside a null state does not necessarily mean that it is in the overlap.
No, does not necessarily mean. It might or might not be.
Right.
That's something you have to check. Okay? Now, there is an easy way to check here. Because we know the dimensions of the primaries of the, the second level primaries. Let's work them out. Is this clear? Okay. So, let's work out the dimension of
Null states in these null states.
exactly.
What's the product of it?
Exactly. So let's write it down. Now, the only difficult thing about this exercise is there are so many different ways of writing it. You have to find the right identities. So that's why I'm going to. Did I bring that book? Yeah. I'm going to write down what they write because that makes it easy, and then we will see that it's right and see that it. Okay. So. Maybe I'll write here. First, let's look at. First, let's write down this guy. These guys like to write these inclusion formulas. I'll follow them. RS. Okay. The way they like to write what the null states are is in this way: subset of. So it's just notation, but just so that you see this notation. Take the original primary. I want to write the null content of the original primary, right? So this guy, they like to write it as V of P prime plus R P minus S union V of R to P minus S. Okay, let's check that this is correct. Okay, you see, it should be one of these two and one of these two. Which one, of course, doesn't matter in the end, because they're the same numbers. Okay, but it should be one of these two and one of these two. So let's look. This was P prime plus R P minus S. So this guy was this guy, and R and 2P minus S was this guy. Okay, so that this is true is obvious. These are the primary labels for the null states of the original multiplet. Clear? Okay, now we want to see what are the labels for the null states of this guy. Okay, this guy has two sets of null states. And we want to write down what are the labels for the null states of this guy. It also has two sets of null states. Clear? So I'm going to write it down and then we'll check. claim V of P prime plus R P minus S, the first guy, this has the following two as null states. V of 2P prime plus RS and union V of R 2P plus S. Let's check that this is the case. We have to keep our wits about us, okay? Because P prime is P prime. Where P prime and P label the central charge of the theory, for instance. And that's not changing when you go to your null state. P prime is P prime. What is this if the new effective R in this case is P prime plus R? Okay, so let's get this guy. That's this guy. Because you add P prime to the new effective R, so you get 2P prime plus R. Yeah? And for this, you take P and subtract it from the new effective S. So P minus S, so that's S. Clear? Okay, now let's get this guy. It has to be one of these two. Let's see. It has to be one of these two. It's certainly not R. Which one does happen? Oh. Why is this wrong? Sorry. Just a minute. What's this one? It looks like this guy is this guy, right? Right, because you get P prime minus R. So this P prime minus P, what am I saying? P prime, sorry, just a minute. Where is this coming from? Right now, we're just finding the null states of this guy, right? But it should have had the two different kinds. This kind, one of these two and one of these two. This is working, right? But that I can't see. Sorry, maybe there's a typo in the book. Just a minute. You agree this guy works? Yeah, because we just take 2P. We take P minus S. No, first form. Yeah, no, but we're changing the PQ labels in this formula. We're not just looking at the level. We're looking at the shift of the PQ labels, PP prime labels, P prime P labels. Right? These formulas I think are correct for the shifts of the levels. We got this and then we put it in terms of PP prime. I mean, sorry, RS, the RS labels. Okay? So we've got, this is the new R, this is the new S. Okay.
The shifts of them will be given by P prime plus that R
Yes,
and P plus that S.
exactly.
Correctly working, no? Because we get
For the first one, we get P prime plus this R.
okay, it's P minus. Sorry.
Okay? And P minus this S. Here it's P minus S. Right? P prime plus R, P minus S. Let me check if I've got the formulas right. Sorry. P prime plus R, P minus S, P prime minus R, P plus S. And R, 2P minus S, and 2P prime minus RS. Okay, this one it seems to me works. Do you guys agree? This guy gives this, but the other guy should have been from down here. And I'm not seeing that. Just a minute. Okay, let's put this aside, go on to the next guy, and maybe there's a typo and we'll fix it. Okay, we'll just, of course, work with what is correct. Oh, it should work. Okay, coming back to this. Okay, let me write the second thing they write. V R 2P minus S. I'll write their formula and then we will see. V of, oh, maybe they use some periodicity. Maybe they use some periodicity. Just a minute. Just a minute. So let's see. Let's use one of these. So let's say we use this guy. Let's see. Let's get the R dependencies, right? R dependence. He has an R plus R. Let's say we let's say we use this guy. Okay, so this would then be V. We would get V the same R, so P prime plus R, and 2P minus S. So P plus S. 2P, oh, 2P. Two P minus S, right? So 2P minus P, so P plus S, and it's like he added a P prime, subtracted a P prime from here, and added a P prime to this. The periodicity was adding both, right? Something looks wrong. Okay, sorry for this. Let's work out the other guy and come back. Or we'll just do it ourselves. Let's write out the other guy and come back.
After doing periodicity, it seems it's giving again HRS.
HR. Which one? This one?
According to that formula, you could have got V P prime plus R, comma V P plus S, right?
Which formula are you using? This one or this one?
The second, middle one.
This one. Okay. So what we would have got, let's see. So we just take R. So V P prime plus R and P plus S, which as you say is same as VRS. Yeah. Which is okay. I mean, these things cycle around. Maybe it's correct, just. But it's odd. Okay, I'm going to work out the other guy and see how this is working. Sorry. Just one last. Have I written some formulas wrong? R into 2p minus s, 2p minus r s. Just check, this was also in the previous chapter. Okay. Okay. Let's leave this. Let's go to the next guy and see. Okay. The next guy he claims is the following. We are.
Is there any reason we need to keep track of these labels, and why don't we just choose anyone we want and then
Yeah, we could just choose anyone. I just would like to match the book. Yeah, it's true. We can choose whatever we want. Yeah. Oh. Because the book in the end will give the right answer. Right? We don't want to, we don't want to prove something. Yeah. It's a bit dangerous. Yeah. But okay, we will in the end eventually do that if we cannot get this. Okay. Okay. Let's look. We are 2p minus s. The subset of this is claim V of p prime minus r 3p minus s union V of 3p prime minus r p minus s. P minus s. Let's see, does even this work? First one works from this side. So p prime minus r, good. And p plus s. Yeah, because p plus this, exactly. So this guy is okay. It is this fellow. Okay. Now does the second one work? 3p prime minus r. This is also not working.
I think for this we have to use the second periodicity condition. P, no, this p prime minus.
So we'll get this. We'll get from the second. Yeah. So we'll get 2p prime minus r and s, which is 2p minus s. And somehow, once again, he's raised p prime by 1 and lowered p by 1. I didn't think that was a period. Let me see if that is somehow.
So second and third answers have the only periodicity. Using the periodicities in the first.
I mean, you can always shift overall by p also. We can shift. Yeah. It's just 1 minute. I'm missing something stupid. Please excuse me. Okay. Okay. Sorry. And just 1 minute, I'm really sorry about this. Just 1 minute more and then. P prime minus. Okay. One thing that we can see is that these two, I wanted to show, we'll do it with what we actually get, let's try. I wanted to show you that these two null states of the null states were actually the same. That's what I wanted to show. Let's check that these two, the ones that we have actually calculated, are equal. Okay, so I'm going to use this, on this guy, I use the following periodicity property. P prime minus this and P minus this is the same as this guy. So that's V of minus P prime minus R and P minus this, P minus S. So this is equal to this. But now add 2p and 2p prime and 2p. So this becomes V of P prime minus R and 3p minus S, which is the same as this guy. Okay. Now, as you suggested, let's just use what we think is right and see if what. These two are also related, except that okay, let's see. This, if we did it, we'd get P prime minus R and minus P prime minus S. P prime. And then once again, by pushing two levels, these two would be related, except that we haven't managed to show that these are the right ones. Right, so it's true that these two are equal. Let's check what we are getting. And so I'm missing something stupid. Let's check. What we would get is here V of P prime minus R and minus P minus S Now add 2p prime and 2p. So that becomes 3p prime minus r and p minus s. So these two are also actually equal. The whole point of this exercise was to show that these two null states were equal. Except, okay, let me just 1 minute do it from what we get. Okay, so as, I mean, we can use anything we want. So let's just use the first one on p prime minus r and p minus s. Let's use the first one. So what do we get? We get v of r to p minus s. P plus r and p plus s, which is v of rs, as you said. Okay, and let's do the same thing on this guy. So we'll just use the first one. So that's v of r and 2p r and s. Okay, so they are equal. It's just that I'm not matching the book, which makes me uncomfortable, but forget the book for now. Okay, so what we have seen is the following. We have seen in terms of the diagram, we had these null states. Each of them have null states, and now I can't draw this because they overlap in two places. But each of the null states, there's a second one, are actually the same. Okay? And if you iterate this exercise, you find that it always continues.
After 2 steps.
Okay? So you see, the first we started with one primary. Then we had, that primary had two null states. So you might have thought that actually there are 4 null states at the next step, because each new primary would have its own 2 null states, but actually they're the same. So the next step also you have 2 primaries. Now we have to look at those primaries and see if their null states overlap. Turns out they perfectly overlap. So again at the next step there are two null states, and so on. Okay?
So these things that the things that we have not shown are equal will never be equal for any special cases of PP prime also.
What do you mean are not shown are equal?
I mean, we have shown that these two are equal.
There's nothing else that could be equal because the null states have matched. You see, what was the question was, were the null states of the null states overlapping? Now both null states of the first null states overlap with both the null states of the second null states. There's nothing left. It's perfect overlap. Okay? Exactly. So now what do we have to do? Because of this overlap, now by subtracting the long character of the null states, we're doing too much. Because we're subtracting the null states of the null states twice. So at the next level, we add the primary, the long character of the null states of the null states. But now because those guys overlap, then we subtract their null states and add again.
And how do we know that there is nothing else common?
Because only things that can be common are null states.
Because otherwise you can
Just come down. Yeah, the question of which primary you are in is unambiguous unless you've got a null state. Yes. No, but you can just check the numerology. We know all the numbers, right? So you can check at the next level. You just like we checked, and I'm reluctant to try to do this because we spent so much time doing it, but it happens, right? It's just a simple check of numbers. Okay, you can check it inductively if you like. Okay? And this happens. And therefore, the character has the following structure. Chi p prime rs is equal to chi long h rs minus two characters. This will be at h rs plus h rs plus rs and minus the character at h rs plus p prime minus r p minus s. Okay? Then plus two characters. Okay? Plus characters at the null states of this guy, which is the same numbers as the null states of that guy. Okay? Minus two characters and so on. So you just keep going. Okay? So you can write this very explicitly and sum it up and so on to get a very clear character formula, just because we've got explicit expressions for each of these chi longs. All this is long. Is this clear? So chi is original chi minus two chi's plus two chi's minus two chi's plus two chi's, and just keep going. All of these chi's are long chi's. Okay? I won't write down an explicit formula for you. After this, it's clear you can do it, right? Okay? But it's just this character formula is very explicit. People, they write in terms of eta prime function, whatever, some crazy functions, very explicit. You could calculate it yourself. Okay? And tells you that you understand the structure of the short representations completely. You know the states of the short representations as well as you'd like to. Okay, that's all I wanted to say about these characters. I'm sorry I couldn't reproduce the formulas in the book. I somehow feel it's unlikely they've made a mistake. Something I'm missing. But anyway, if this has mistakes, okay, maybe this is one of the mistakes. Okay. Okay. Excellent. Yes.
These second quantities, they were coming out to be equal to VRS, the thing we started with.
Yes.
So,
Yeah, also that sounds funny, right? It sounds, I have to say, it sounds funny. Somehow I feel that the result that the two things match is correct, but I feel that with the, okay, let me tell you what, this guy writes down an explicit character formula for he has rs minus p prime plus r p minus s minus r to p minus s. This we agree with. Then his next ones are plus 2p prime plus r s. It's that same thing there. 2p prime. Oh. Well, let me write it down. 2p prime plus rs and r 2p plus s minus, and then it just keeps going. This is what he had. You're right that in what we did, we had p prime minus r and 3p minus s, which is oh. I wonder if there's some minus signs I'm not thinking. Okay, let me try to get. Let me by next class I will try to reproduce. I will try to clear up any confusion we have about this. I feel somehow that there is some. When this thing's going negative, you have to make it positive. Some business like that must be going on, right? Let me clear it up next class. I'm confused. Yeah. Yes. A little louder.
Are these things somewhat giving us irreducible?
The whole thing is an irreducible representation. The whole thing is the representation of our module. Okay, we have written the irreducible representation of this guy as an alternating sum of long representations. Yeah. If you think about it, we don't normally think about it this way, but in SU2 theory also you can think of it this way. You can think of a general representation as being built by starting with the highest weight and acting with j minus an infinite number of times. But now this representation has a null state, which is at the bottom of this. Okay, then you can subtract away what happens from the null state. In that case, it's very simple, because you just subtract away everything that you get built out of the null state. So you just have j minus going down to the null state and stopping. Okay, but once again, SU2 character is a difference of two long characters. Okay, so this is very generic in representation theory, that you can write any character as sums and differences of long characters, because what you're doing is what you would have got, then removing null states. Okay, but this is the final answer for an irreducible representation. Okay, but as you say, I'm not totally confident of our numbers here. I will try to clear that up by next class. The structure is correct. Okay. Okay, let's move on. Okay, we now want to move to the second technical topic that we want to discuss. And the second technical topic that we wanted to discuss was the explicit construction of null states. Okay, so what are we going to do? We're going to produce, okay, this is quite a Baroque construction. Okay, it's a construction that I think you would have a hard time thinking up yourself. Okay, but it's easy to check that it works. I hope it's easy to check that it works. I presume the book's checks were correct, but let's see. Okay. Okay, so the question we're going to ask is the following. Suppose we take the representation module VR1. We're looking at VR1 rather than VRS because the construction is simplest in this case. Simplest, most explicit, and so on. Okay, I'm now going to outline a sort of crazy sounding construction of the null state, so you'll have to bear with me. Okay, so the question we want is this. We know that this guy has a null state at level R, because it has a null state at level R times S, where S is equal to 1. So we have a null state at level R. Okay, so our null state is going to be, some combination of L minus 1 to the power R, L minus 1 to the power R minus 1, L minus 2, then L minus 2 squared, L minus 1 to the power, whatever, R minus 4, R minus 2, L minus 2, and R minus 1 and R minus 2. Sorry, L minus 1 to the power R, L minus 1 to the power R minus 2, and R minus 4, and so on. The net sums of the weights have to be R. Partitions of R. Right? So there is going to be some linear combinations of all these guys. Question is, which linear combination? Okay? There is a very simple construction. It looks like a very complicated problem, right? Because there are many basis states. Remarkably enough, there is a very simple construction of this null state. Okay? And the simple construction goes as follows. First, we study and we just make some definitions. Okay? And the definitions go as follows. What we're going to do is to make we're going to define a collection of 3 R cross R matrices. Okay? We will suggestively call these J0, J plus, and J minus. Okay? We will call them this because these 3 R cross R matrices will, the commutation relations will be that of SU2 in spin R minus 1 by 2, the R dimensional representation of SU2. Okay? But these matrices will not be the usual matrices we work with in quantum mechanics, they're closely related. Let's look at them. So J0 is defined by J0ij. J0ij is equal to half of R minus 2I plus 1. Okay? And if you look at this, so I and J run from I and J run from 1 to R. Okay. So let's look at it. Let's look at it at I equals R. At I equals R, we have R minus 2R plus 1. So at I equals R, we get minus of R minus 1 by 2. At I is equal to minus R, we get at I equals plus 1. Sorry. R minus 1. What am I saying? R equals 0. R equals R equals 1, right? R equals 1. We get R minus 1 by 2. So the range of I goes from 1 to R. Okay? So if you write down this matrix, it is block diagonal, and we have R minus 1 by 2, R minus 3 by 2, minus of R minus 1 by 2. This is the usual JZ matrix for when the spin is R minus 1 by 2. Okay, so that's what this JZ matrix is. Now J plus is defined as equal to, let me give you J minus first. J minus is very simple. It's equal to J minus Ij is equal to delta I J plus 1 for J is equal to 1, 2 up to R minus 1 and is equal to 0 for J is equal to 0. Okay. So this matrix is very simple. It's just got a bunch of ones. You know, this first row is zeros and then it's got ones like this. Right? The last column has all zeros. That was what this guy was saying. Okay? So what does this matrix do, this J minus? If you had, suppose I was acting on something like this. Okay? If you have something here, this guy will act on it and bring it down. Okay, so J minus takes a column and takes every element on the column, brings it down. Okay, it's a lowering matrix and just brings it down without any additional scaling.
The states I suppose are not normalized.
What?
The states of this representation I think are not normalized over them. Because usually they have this
Yeah, it's that the yeah, it's like you're taking the bras and you know what we're doing is taking the normalization and putting all of it inside J plus instead of some in J minus, some in J plus. Okay, so what does that mean in terms of states? It would mean that the states are normalized in a different way, exactly, because J plus and J minus relate different states. 1 to 2, so if you change the normalization of 2, you can fix that, exactly.
But nevertheless, these will satisfy the
SU2 algebra, it's just that J plus and J minus will not be Hermitian conjugates of each other with the usual notion of Hermitian conjugation. As Chintan said, with the appropriate inner product, they will also be Hermitian conjugates of each other. It's just not the inner product's just not 1, 1, 1, 1. Yeah. Okay, and finally, we take these this J plus is equal to I into R minus I into delta I plus 1 J. Okay. So first thing to say about this J plus is that its elements are all non-zero only here. Right, it's one away from the diagonal, as in the usual J plus. Because its elements are non-zero here, what J plus does is take an element from a column and raise it up. Okay, so in particular, it's this and it's 0. 0 if I is equal to R. Okay, so because it raises things up, the last column will always be 0 when you act with this guy, right? And it gives it with some numbers so as to make sure that it obeys the SU2 algebra. Okay, so for instance, in the case that R is equal to 4, these numbers are the following, just to have something concrete. The numbers are 3, 4, and 3. So then it's a 3, 4, 3. Okay, some numbers. Okay, so these are these matrices that we're going to look at. Okay, now what are we going to do with these matrices? I don't think we're going to have need for this anymore, so let's take this up. With these matrices, we define the following thing. D R comma 1 T. T is the T from P prime by P. Okay. D R comma 1 T, we define this to be the following. We define this to be minus J minus, okay, plus sum m is equal to 0 to infinity minus T J plus to the power m L of minus m minus 1. Okay, so now what is this object? It's an object that acts on the tensor product of R columns and states in the representation space. The LMs act on states in representation space, and the J plus J minus act on this R column. Okay, so you can think of it as acting on an R column, each entry of the R column being a state in representation space. Okay, Now, this looks like an infinite operator because of the sum m is equal to 0 to infinity. But clearly, j plus to the power r is equal to 0 because j plus raises. You keep raising, and finally, there's nowhere further to go. Okay? So, though the sum is written m is equal to 0 to infinity, we can replace this by r minus 1. Right? Because j plus to the power r is 0.
What if you consider infinite dimensional equivalent?
Infinite dimension, but r is r. You see, we are looking at the module h r comma s. So r is some number. What are these? This is just some formal operator.
But each state has some label corresponding to this.
Yes, it's a formal operator acting on a column. Each element of which is some state in representation module. What we're going to do with it, you'll see. At the moment, just formal mathematics. Okay. Now, we ask the following question. So we take this dr comma 1 and we let it act on r states, which we will call f1, f2 up to fr. Okay? And we're going to try to solve the equation. This is f0, 0, 0, 0. So what's the structure of this problem? We have r plus 1 states. Each of these are states in representation module. f1 to fr and f0. Okay? We want to act with this operator dr comma 1 on the first r states and produce the r plus 1th state, f0, and 0 everywhere else. Okay? This is an equation we're going to study. Okay? Now, let's look at this equation. See, clearly if we wanted to use this to solve for f0 in terms of these guys, that's already done. f0 is this differential operator on those guys. Right? What we're going to do is something funny. We're going to use this system of equations not to solve for f0 in terms of these guys, okay, but instead to solve for fr in terms of f0. Not the others. The others are all going to be determined because you see we've got, the way you think of it is you've got r equations for r plus 1 variables. Right? Each column is an equation, each row is an equation. So I've got r equations for r plus 1 variables. So I can use these equations to solve for, all of them in terms of 1. Okay? And I'm going to try to choose that 1 to be fr. So I will solve for all of the variables in terms of fr, f1, f2 and so on. But in particular, I will solve for f0 in terms of fr. Okay? We're going to solve for it in a moment, but let me first tell you where we're going. So this thing will give us some linear solution. f0 is equal to delta, whatever the answer to this problem is, some linear operation. We define this as delta on fr. Okay? The claim we're going to make is this, that if we replace fr by the primary state, then f0 by a descendant will be a descendant. We define this delta by this procedure, and the claim we're going to make is that if we act this delta on the primary state, that gives us the null state. Is the claim clear?
So in the terms of this
This delta, we'll have to work out what it means. Okay? Whatever it means, whatever it gives us, one of the first things we'll have to show is that it's all things of the right weight. That they all have weight r. That it's either L minus 1 to the power r or L minus 1, Okay? And the claim is that that operation, that state that we get, that linear combination of these L's, is the correct null state.
So FR is the primary and
F0 is the descendant. The null descendant. The null primary.
others are something different.
The others, no interpretation. They're just part of the procedure. The final answer is only F0 as a function of Fr. Okay, this is the claim. Okay, and if we did the same thing with instead of doing it Rs, but P prime minus R, P prime minus S, we'll get the other null state. Okay. Now let us study the structure of this operation a little bit. Just to make sure that we are understanding what's going on. What do you mean the other null states? It's the same operation. Yeah, because the null states are themselves reducible representations of the same kind. So once you know for one guy, I mean, provided it's R comma 1. Okay, there is a generalization of this procedure to R comma S. Right? That will just, it has higher group and has iterative structure. If you want, we can in the next class look at that. It's very complicated. But okay, it's explicit. Okay. Okay. Fine. So, but just let's take this object and look at it a little bit. Let's look at this dr comma 1 a little bit first. Okay? So let's just write out this dr comma 1. Oh, sorry, I should have. Op that produces null state from primary. Okay. Okay. So let's take this dr comma 1 and look at it a little bit so that we understand, look at its action on F1, F2 and so on a little bit. Okay, so let's take dr comma 1 and explicitly see what we get when we act on F1, F2 up down to Fr. So first we have minus jr. Okay, that just lowers. Okay, so minus j minus on F1 down to Fr is equal to 0 minus F1 minus F2 minus Fr minus 1. Right? Okay. And what about j plus to the power m? Let's first do j plus. J plus on F1 Fm. This, now not keeping track of numbers. Okay? This guy raises. So this gives us F2, some numbers. F3, this was R, sorry. Fr0. And if we did it m times, we did it once, we have, so if we did, so j plus to the power m on F1 Fr is equal to F1 plus m F of 2 plus m Fr and then 0, 0, 0, there will be m such zeros. Okay, fine. Now we want to act this j minus plus a linear combinations of all these guys and produce F0 down to 0. So we want to do this. So what we want to do is to start solving for all the states in terms of Fr. Now the easiest equation to look at is the one in the last row, because the equation in the last row has only two terms, because remember that sum there went from m is equal to 0. Okay, so when we had j plus to the power 0, we had Fr in the last row. Okay, j plus to the power anything else produces 0 in the last row. Okay, but j minus produces Fr minus 1 in the last row. Okay, so up to some numbers, you look at the last row and you'll get Fr minus 1 is equal to some number times Fr. Okay, except that we have to keep track of the L's. Since we were the only one that contributed here was m equals 0, there we get L minus 1 Fr. Is that clear? Okay. Now let's look at the second last row. Second last row gives us Fr minus 2 is equal to some number times L minus 1 Fr minus 1 plus L minus 2 of Fr. Okay, but Fr minus 1 was already L minus 1 of Fr. So this will give you some number times L minus 1 the whole thing squared plus some other number times L minus 2 times Fr. Clear? Now we do the same thing with Fr minus 3. You see how it's going, right? We'll get an L minus 1 cube, an L minus 1, L minus 2, and so on. You see that as we keep going up, the dimension, each time we go up one row, the dimension of our state increases by 1. And so when we go up all the way up to the first row, the dimension of the state has increased by r. Yeah, I mean, the first row it's r minus 1, and then when we relate that to F0, it increases by r. Right, because this j minus term does not contribute in the first row. So it's only the j's that contribute. Okay, so you go there, you increase by r. Okay, so you see that this operator that we get when we write f0 in terms of did I say it the other way around? Maybe I said it. Yeah, f0 in terms of fr. I solved for f0 as a function of fr. Okay, when I did that, I get dimension r higher than f0. Okay, so clearly what we get, okay, clearly what we get is a state of the right level to be this rth descendant. Okay, now the question is it really a primary? Okay, so the question is it actually annihilated? Is it actually annihilated by L1 and L2? Okay, so that's the next question we have to address. Once it's annihilated by both L1 and L2, it's a primary. Okay. 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 Now, what? Okay. Okay. I'm going to make a claim. Wondering whether we have enough time for this today. Okay, these two proofs are a little complicated. I suggest we just take them up next time. Okay, they will get. Okay.
What are the theorems that
But we just want to show what we have to do is to actually look at the construction, right? So we look at this construction which is delta on H, the primary. We want to show that L1 on this is equal to 0 and L2 on this is equal to 0. The way we're going to do it is actually along the lines of what Chintan suggested. We're going to construct not just L0, but we'll construct we'll construct the state chi r minus 1, chi r minus 2, and so on. Then we will find a formula for what L1 does on chi r minus 1, on chi m. Okay? And then find a formula for the final answer in terms of these chi m's and show that it has the properties we want. Okay? But it's going to take a little time. I think we'll put that to do. Okay, it's actually not hard algebra, but let's do that next class. Okay, yeah, fine. So next class we will continue. We will complete this, and I will also clear up the confusions we had about these null states, and then we will turn to these fusion rules and differential equations. Okay, I think with luck, by the end of next class, maybe half of the subsequent class, we will have completed chapter 8. Then we will turn to the study of modular invariance in these theories and single valued, constructing correlation functions in a single valued way and so on. Okay.